Hello everyone, this is lesson 2, chapter 6, kinetics. We speak today about the collision theory. Let's get started. For this lesson we have some objectives. Describe and explain collision theory, define activation energy, understand the factors that affect the rate of the chemical reaction, understand the relation between the average energy of particles and the temperature, sketch the Maxwell-Boltzmann energy distribution curve. Now we would like to speak about the chemical reaction in terms of the collision theory or the kinetic theory. First of all, you have to imagine that we have these two reactants. Okay, for these two reactants to react, what are the requirements that are needed for them to react? If we have reactant A, reactant B. Of course, it's obvious that everyone will say that they have to collide. So they have to collide for them to react. This is number one. This could be the first requirement for any reactant to react. What is next? As you already know that everything is surrounded by electrons. Electrons are negatively charged particles. So if A is surrounded by electrons and B is surrounded by electrons, what will happen if they manage to collide? Of course, they will repel each other. For that reason, those particles or those reactants must have the minimum energy to overcome this electron cloud. This energy called the activation energy. So again, the activation energy is the energy required to overcome the electron cloud repulsion. The electron clouds here and in B and the electron cloud in A will repel each other. So there must be an amount of energy supplied or gained by the reactants, giving them the opportunity to react. Okay, so we have said the first requirement is for them to collide. Number two, they have the energy required to overcome the electron cloud repulsion. Number three, if they collide in the correct alignment. They have to collide with the correct alignment, because if you have a pen and you would like, this is just imagine that this is a pen and you would like, let's say this is a cap. Of course, if they collide in the wrong direction, you will not have the cap on the pen, and they must collide in the correct alignment. So the requirements for particles to react are: number one, particles must collide; two, particles must have enough kinetic energy to overcome electron cloud repulsion to react, which is called activation energy. The third requirement is, as we just mentioned here, the reactants must collide in the correct geometric alignment. In the previous unit, we were speaking about the exothermic and the endothermic reaction, and we have said that we have two types of energy profile diagrams. For this one, we have here reactants, we have here products. It's clear that this is endothermic reaction. Why endothermic reaction? Because the products have higher energy than reactants. While on the other side, we have here reactants, we have here products. So this is exothermic reaction because the products have lower energy than the reactants. And of course, obvious that delta H is the difference between products and reactants. In the endothermic reaction, delta H is positive. For the exothermic reaction, the delta H is negative. Let's check our example that we have here. This is obvious that it is an exothermic reaction because the products have lower energy than the reactants. And delta H, of course, is the difference between products and reactants. It has a negative sign. We have something extra here, which is representing the activation energy, the minimum energy or the energy that should be supplied to the reactants to allow them to react. What is the activation energy again? It is the minimum energy required to start a chemical reaction. Why this energy need to be supplied to the reactants to overcome the repulsion caused by the electron cloud surrounding the reactants. How I should calculate it from the potential energy profile? It should start from the reactant till the highest point in my graph. This will represent the activation energy. We have to be clear. We have to always focus on this point, because for endothermic reaction, here is it. It's a bit higher than the exothermic reaction. So as you can see here, the activation energy here is much higher in the endothermic reaction, is much higher than that of the exothermic reaction. But how I should determine it? Same for any type of reaction. You should start from the reactant till the highest point that you have in your curve. We have four factors that affect the rate of the chemical reaction, which are concentration, surface area or particle size, temperature, and catalyst. Let's speak about each one of them. Now let's speak about the four factors that will affect the rate of the chemical reaction in details. First of all, we have four factors: concentration, surface area, temperature, and the catalyst. Speak about the first factor, which is the concentration. Let's imagine we have two scenarios: scenario number one, scenario number two. You know, the chemical reaction is like a fight. Whenever you have a fight with lots of participants, the fight will end very fast. Why? Because you have more collisions, more collisions. Same idea here. When you have first scenario, second scenario, for the second scenario, we have lots of reactants, highly concentrated sample. So you just have to predict that this reaction will be much faster. So when you are increasing the concentration, increase the rate of the reaction, because of the collision frequency is higher. Increasing the pressure, same idea as increasing concentration. We refer to concentration when we are speaking about solution. We refer to pressure when we speak about gaseous reactants. But the effect is the same. When you are increasing the pressure or you are increasing the concentration, you are increasing the frequency of the collisions, or the collision frequency is higher. So as the pressure is increased, the collision frequency increases. The second factor we have here is surface area. Let's imagine that you have a sugar cube and you have powdered sugar. Which one do you think will be dissolved faster? It's of course the powder. Why the powder? Because there is here a large surface area, a higher probability for the particles to contact with the other reactants. Other than this sugar cube, the particles which are inside are waiting for the particles outside on the surface to react first. Then the particles inside this cube will take up their turn. For that reason, if we have two scenarios here, scenario number one and the scenario number two, of course, in the scenario number one, we have a big particle for the reactant. Scenario number two, we have this big particle, but split it into four pieces. When we have those four pieces, the reaction will be, of course, faster. Why is that? Because increasing the surface area, increasing the area for particles to contact, therefore increases the collision. This is the most important point here. The collisions will increase when you have a larger surface area. Number three, temperature. When we speak about temperature, we have to refer to our energy profile diagram. Let's say that we have, here is the reactant and here is the product. This is representing the activation energy. Okay, let's say that the energy of the reactants here is 100. What if you supplied heat, increase the temperature for the reaction? You instead of starting from 100, you would start from 200. So what has happened is, so this is, let's say that this is the condition number one, condition number two. So you already supplied an amount of energy that is needed to start the chemical reaction. So we can say that increasing the pressure increases the collisions. Why? Because you are increasing the number of particles that will have sufficient activation energy to react. Okay, instead of starting from 100, you are starting from 200. So particles have a higher energy, so the activation energy needed will not be that high. The fourth factor is a catalyst. Okay. When we're speaking about the catalyst, we have to imagine that, let's say that we have a mountain. If you'd like to go to school, you have to climb a mountain. Just imagine that. If the government are good enough to dig a tunnel in this mountain, are they going to decrease the height of this mountain, or they will just provide an alternative pathway? Of course, they will never affect the height of the tunnel. For that reason, the activation energy, the original activation energy, will not be affected, but the catalyst will provide an alternative pathway for the action to proceed faster. For that reason, we have to consider, as you can see here, allow the reaction to proceed by an alternative pathway of lower activation energy. Therefore, increases the number of particles that have sufficient energy to overcome the activation energy. We have here this diagram, which is very, very, very important. As you can see here, we have two pathways. We have uncatalyzed pathway and catalyzed pathway. Of course, the catalyzed pathway is shorter. This pathway catalyzed required lower energy than the uncatalyzed pathway. For that reason, the catalyst is increasing the rate of the chemical reaction for its ability to provide an alternative pathway for the reaction with a lower activation energy. It's not 100% correct to say that it will lower the activation energy, but sometimes they use it. When we would like to speak about the Maxwell-Boltzmann energy distribution curve. It seems strange, but it's very easy. Why it's very easy? Just imagine you have a balloon. This balloon has particles. Do you think all these particles have the same energy? Of course not. Some of them will have high energy. For that reason, here in our graph, we have number of particles with kinetic energy, and here's the kinetic energy. So let's imagine that in our balloon here, we say like a small percentage of these particles, they have energy higher than the activation energy. So they are ready to react. The blue area shows the proportion of particles in the sample that have enough energy to react. While the big percentage, the white part, shows the particles that do not have enough energy to react. Now, what will happen? What will happen if you increase temperature? What will happen if you have here something that will increase the temperature of the system? What will happen to the particles? Of course, more particles will gain energy. So what will happen to this graph? What will happen to this graph? More particles will move to this side. So we will see that. You see here in the red graph that we still have the same amount of particles, because this is representing number of particles. We still have the same amount of particles. For that reason, the graph will stretch to the right, because more particles have the minimum energy to react or have the kinetic energy than the first scenario for lower temperature. But what will happen if you are introducing a catalyst to this reaction? As we said before, it provides an alternative pathway for the reaction with lower activation energy. As you can see here, the activation energy, the original activation energy, when you are introducing a catalyst, the activation energy will be, of course, lower. So this is activation energy when we have a catalyzed, okay? And it could be clear here in this graph. With a catalyst, the activation energy needed is much lower than the activation energy when we are having the reaction without a catalyst. Thank you for watching this video. Stay tuned.